Well, hey everyone. A lot of you know who I am. I'm Alex. I am the previous organizer of Nashville DataNerds. As most of you have seen in recent posts, I made the decision to step down as the organizer of Nashville DataNerds to kind of pursue some other community-based projects. But wanted to, thank you to Glenn for giving me this time. I really wanted to take this time to say that it has been my pleasure to kind of lead this community over the past 3 years. Thank you to everyone who has led conversations. Thank you to everyone's showed up when we met in person and when we transitioned to Zoom. And we all worked through that together. But I can't imagine a better person than Glenn to take over Nashville DataNerds and lead it into its next iteration. I met Glenn a couple of years ago. He's been someone that's helped me in my journey in data. And he continues to help so many people in the greater Nashville area in their journeys in data. So really excited to see what Glenn has in store for DataNerds. And a nice surprise, we actually have the OG data nerd, JohnBerryman, with us. So we have 3 generations of DataNerds organizers here tonight. But anyhow, thank you, everyone. Looking forward to becoming a member.
And thanks, Alex. And I am stepping into but yes, Scott's kind of giving Alex a hand, and also John. And I don't know if you understand. So John started DataNerds, and I couldn't remember earlier. Do you know which year it was, John?
1987, if I remember correctly. I don't know. It's probably when I moved to Nashville, so about 7 years ago.
Okay. And I'm not sure if DataNerds is what brought us together. Anyway, I've known John for several years, and we've really become good friends as with Alex as well. And this is an honor to follow them. I appreciate that. I am all about building community, and so I hope that I can continue to do that. I would love for us to be kind of more than just a monthly meeting. No requirements, but I want to find ways for us to engage with each other, not just with a speaker, not just with me. I'd love for you guys to get to know each other, and I will be try to be helpful in building some of those bridges. My wife says if you're looking for me, I'm in a coffee shop somewhere in Nashville, and so I plan to continue that and help you with your career, professional development, or mainly just meeting the other good people in the room. I won't spend too much time talking tonight. I want to make sure that we give John most of the time. We've talked about Alex, myself, and John. John, you've got a real treat here. Again, the founder of DataNerds. He's now a senior data scientist at GitHub. You've probably read his bio. He started out in aerospace engineering. And soon found that he was more interested in math and software than in satellites and aircraft. You can read that. I've just found John to be a wonderful friend, a brilliant mind, wonderful parent and husband, and all those type things. He's just a good person that you should know. And so I'm going to turn it over to him in just a bit. I will make mention that, basically I'm paying for this. Acre Consulting is the sponsor for DataNerds from this point on. Maybe a little later, I'll tell you what I'm trying to do with that. Penny University is associated with DataNerds as well. One thing I do want to push that Alex set up was the DataNerds LinkedIn group. And I would love for you to connect there or connect with me so that I can help you. I can get to know you a little bit better, but also help you with your connections in the data community. So please reach out to me and to the DataNerds LinkedIn group. As I said over and over, I'm eager to connect with you, but also to help you connect with others. And then finally, what we're about to do, we're going to turn this over to John. He said that he's going to have Elasticsearch in an hour, but we're going to compress it to 45 minutes. I will be looking for your questions primarily on chat. And so if you'll use Zoom chat to ask questions throughout the presentation, I think John would like some interaction, and that might be helpful. Post your comments. I'll try to find a time that seems natural to stop him for a moment. And then at the end, we should have some time for questions as well. Any questions, comments before we get started? All right, forgive my rambling. I'm going to stop sharing and let John take over here, and it is all yours. Thanks for being here, John, and to everyone.
Then I will share my screen and we'll get going. There's my slide. Here we go. All right, so Elasticsearch in an hour or 45 minutes or however long it takes. You know about me already. My name at GitHub is JohnBerryman. I didn't know that that would be my permanent name forever, but that's what we call each other by at GitHub. So that means my name. I was a pretty nerdy kid, got into aerospace engineering. What Glenn didn't tell you is that it took failing out of mechanical engineering to get into aerospace. Long story. Ended up in search technology, wrote a book about it. And so thus we're here today. And then I got to use search a few times, and I'm finally at GitHub. I helped recreate the search infrastructure in a more scalable way. That was my most recent search project. And I've since then moved on to data science at GitHub. All right, so in the next hour, let me get some of the Zoom stuff out of the way. In the next hour, we are going to do these three things. We're going to build a quick and dirty search application. We're going to look under the hood and see how the search algorithms work. And then we're going to kind of give you a glance at what would be like a day in the life of a relevance engineer. And the intent here, bullet by bullet, is I want you guys to have approachability. We're going to build something and you'll see, oh, that's easy. I want you to have some intuition. Someone at work says, hey, can we use search for this? I want you to be able to say, yeah, because the data structures make sense for this, as opposed to, I don't know, it's fun, it's NoSQL. And last of all, with the third bullet, we're going to talk about the practical experience, what it is to work in this field. All right, so the first thing, let's build an app. We'll create an index. We'll install Elasticsearch, create an index, pull in some documents, and write some queries. Approachability. You'll be comfortable. You'll be more comfortable. We're going through it quickly, but you'll be more comfortable to say, okay, I can look back at these notes and repeat what John did pretty easily. All right, a little bit of an eye chart, but no big deal. First of all, first line, we're going to download Elasticsearch. That's what that first line does. We're going to unzip it. We're going to go to that directory and bin/Elasticsearch runs a server. Poof, now we've got a server up and running. If I talk to it, this is an HTTP request. If I say, hey, Elasticsearch, tell me you're awake, then it responds happily, you know, for search. Part of the way there. Next up is creating an index.
John, I'm going to break in for just a second. One of the questions was, what if we don't know what Elasticsearch is?
Good context. Good context.
Thank you. Thank you.
Great context. Elasticsearch is a data storage system. So not unlike MySQL or any of its competitors, not unlike Redis, key value store, in that it stores data, but it's specialized. Like all those data storage systems are specialized to particular needs. Elasticsearch is a search engine specifically. Rather than recording tabular information like a database would, it records documents along with tabular information if there is anything associated with it. And it's made for very quick lookups on the data, the documents, and it's made for the ability not just to, like give you back and like a Boolean match, like this is match this, this, and this, but it gives you back also like score results. So a notion of relevance. All with the goal of helping users to find the documents that they're looking for. So given that, and given that we've got Elasticsearch running, if you were going to use SQL, for example, and you wanted to make a new table, you would specify its schema. That for most people, that's more familiar than a search engine. But with Elasticsearch, you have to do much the same thing. And basically, I will talk to the endpoint. I will say, we're going to make a new index called documentation, and it's going to have this mapping, this schema. It's going to have a title field, which is of type text. It's going to have an author field, which is of type keyword. It's a different type of text. We'll get there. It's going to have contents. It's more text. It will have a public field that is a Boolean. blah, blah, blah. The idea is that you can specify fields just like you would in a normal database. You can specify field types. But the interesting caveat that you'll see plenty of examples of is that Elasticsearch understands text in a way that databases don't. Database just sees a long series of characters. Elasticsearch sees English words or sees, you can teach it whatever you want to based on the analysis process. So now since we have the schema, we can stick in documents. Basically same thing. We say, dear localhost 9200, that's where Elasticsearch lives.
John,
This index, this document, we're going to put a new document in there, and it's going to basically have all those fields populated. This is just an example with text and dates and booleans and stuff like that. And that is half the puzzle. Getting the data in, getting the data out of the search engine is the other thing. People will come to your library, people will come to your e-commerce store and type in a query, but underneath the hood, you've got to do an HTTP request out to the search engine, and here is the varieties that your searches can take. The easiest one, the first search that anyone ever does just to kick the tires and make sure it works, is a match all query. This is effectively, if you know SQL, this would be like select star from documentation. Give me every document back, and it returns results that look kind of like this. It's a JSON blob. I wish JSON was prettier, but it tells you several important things. It says this query took 3 seconds, or actually I think it's 3 milliseconds. This query has 1 total result, and here is the list of results. There's 1 result, and it is just that 1 document that we've indexed. So that's the simplest possible search that you can do, and that gives you an idea about the way that Elasticsearch is going to convey back the results. It'll be the application engineer's job to take all this stuff and stick it back into the UI and make it pretty. So given our document, let's look at real queries that you would make. The simplest such query would be find 1 term in a field. I want to find any document that has John Berryman in the author field. Or similarly, you could say, it seems like a different field type, but you could say true in the public field. Anything that's just 1 token, 1 piece of text in a field, that's a term query. And so that would be a match to this document because John Berryman is indeed in the author field. Moving on up, you can get more complicated queries. So a match query looks like a text query, a term query, except that you can deal with more than 1 term. And it also does some really interesting stuff as far as understanding that this is a field of English text as opposed to just a field of exact string match. So if I wanted to search for sort filbert on filbert sorting for fun and profit, it would match, despite the fact that the capitalization is different, despite the fact that these aren't the same words. It understands that in English, the word sort, the word sorting and its root word sort, you're probably looking for the same thing. It's probably worth returning it as a match.
And John, there was another question, and I think you just answered it. Could you also explain why use Elasticsearch rather than something like MongoDB? And it's because the English rather than the, anyways, just strings, right?
It's because of how it understands English and how quickly it can find documents that match the words you're looking for. Whereas MongoDB is much more naive as far as search functionality. You'll find exact matches and that's it. All right, so if we go to more complicated stuff, you can say, well, here's a match phrase. It has to match exactly this. That would not be a match because these are in the wrong order. But you can reverse the order and it will still match, but notice that it's still dealing with it as an English word. It says filbert and sort are pretty close to this phrase, filbert sorting. It's a match. Filbert fun would not be a match because filbert is way too far away from fun. That's not a phrase. You got all these other words. But even though it's not a match, you can add parameters in there to say, like, let's make it a sloppy phrase match, and you can have up to 2 words between them. And so that would match. And the details here aren't just crucially important, but the idea is there's a lot of building block searches that you can use to make, you can use to express your users' information need and find documents that match. The last building block, and it's really more of the mortar between the building blocks, is a Boolean query, which is the way that you can take all these little pieces, these building blocks, and you can combine them together. For example, in this case, you can say, I want all the documents that must have author John Berryman. They must also have be public equals true. They must also have this somewhere in the title. Order doesn't matter. And additionally, this is where it's kind of like an or phrase. They must match these, but if they happen to match the exact phrase Filbert Fun, then boost that up higher, and that's where scoring becomes involved. And so a bool query in Elasticsearch is a way that you can craft these really complicated combinations of the underlying atomic queries. In the interest of time, I won't go over it, but that is a list of the most commonly used chunks. So that was round 1, approachability. We've created our first search application. Next thing is internals. Search engines, what are they good for? How does the information get inside of them? How are the documents ingested into the data structures? How can the documents be found so quickly? Because Elasticsearch is very quick for that specific type of work. And the thing that I most enjoy, the relevance. How do you teach the search engine what a user's notion of this is more important than that? How do you convey that to a search engine, and how does that actually work under the hood? It's all math, TLDR. And hopefully this gives you a little bit of intuition about when search engines are better applicable versus other data storage systems. So let's start with a sentence that this is the title of a document, for example, and I want to index it. The conspirators conspire conspicuously. In order to get that into the index, we go through a chain of analysis that modifies the string until it's something that's digestible by the search engine. And at the end of this, it looks very different, but the search engine, being a computer, is going to be happy with the results. First thing is tokenization. We take that string and we chop it up into the words. By default, Elasticsearch will split on white space and punctuation, and that's what we've seen here. And the exclamation mark is gone. But in other languages, it might need to be something completely different. Chinese, for example, has no spaces. German, for example, they stick a lot of words together, and maybe the meaning is in the chunks rather than this giant word that no one's ever going to search. So tokenization gets really interesting when you get into different languages. Lowercasing, it's obvious. If I type in lowercase d, I want to match a document that happens to have it capitalized. So that is important for a computer. Stop wording. Maybe I don't care about the at all. These in every document. No one's going to search for it. I don't care. And stemming. This is also kind of a fun way of conveying to the search engine what English is, for example. In this case, we will take the ends of the words and chop them off to get right down to the root. Because if I'm searching for sort or sorting or sorted or any variant of that, probably I intend the same thing. So this is a way to make search easier on your users. They don't have to type the exact word in. Okay, now giving the search engines understanding of this example sentence, we got to shove it into the actual search index. Think of the search index as a key value store, as a dictionary. It's actually not too far from that. And so when we have document 1 and it breaks up into these tokens, all we're going to do is invert it and say, well, this token right here, conspire, it is associated with an array of documents. Document 1 is one of them, but let's say we index other stuff later and it's found elsewhere. Conspicu is a token in the first document, but also several others as well. And as we index more and more and more documents, then this becomes a very large population of words on the left. And like, here is a list of all the documents that contain that word. But that is the secret sauce. That is what makes it so quick to search. And let's exactly look at that. If I have an example query, I'm looking for aardvarks, then how do you quickly, it's like amazingly fast, how do you find all the documents that contains aardvarks? Well, you've already done the work during indexing time. You just go to this big dictionary, you look up aardvark and say the exact answer is already pre-computed for you. It's super fast. And then you can see how you can extend that to more complicated searches. I want to find all documents that contain conspicuous and aardvarks. Well, I go to the corresponding entries here, and I find only the common terms. So 92 is in both of these. And or would be just the same thing, except I union the list instead of intersect the list. But in any case, they're very fast. Harder to do audience interaction here, but which is faster, and or? The answer, since I can't see raised hands, is and. If you've got a lot of words, then basically you're taking these long lists of, like, conspicuous really in real life would have happened in 40 documents, and aardvarks happens in 70 documents. And if you keep adding more and more words to it, the list shrinks down further and further and further, and it's actually less and less work for the search engine to do. It's even faster. All right, and the last bit of search engine internals is how the search engine understands scoring. A human understands, if I type in the Beatles, like, I really don't care about the that much. I do care about Beatles. That's probably what I'm really looking for. And we have an intuition. Computers don't have good intuition. So what we have to do instead is mock intuition. And the way this is done in search engines is a mathematical equation called TF-IDF, where TF is the term frequency, and I'll tell you what that means, and IDF is the inverse document frequency. So let's look at this and explain what this means with an example query. The diddle. My example query is the diddle. And an example document that might match this query is, hey diddle diddle, the cat and the fiddle. Okay, so term frequency is the number of times that each one of these words occurs in the documents that are matches. So the term frequency for the is 2. It happens there and it happens there. The term frequency for diddle also happens to be 2. 1, 2. Easy enough. The inverse document frequency is just 1 divided by the document frequency. That's what inverse means. And document frequency itself means how many documents these words are contained in. Because the idea is, if it's a really common word like the document frequency is going to be super high, and then therefore the inverse document frequency is going to be super low. The is not important. The document frequency for diddle, being a fairly uncommon word, is it occurred in 7 documents in my imaginary index. And so when you convert this to the inverse document frequency, the has an IDF score of 0. Diddle has an IDF score of 1 divided by 7. And the final magic happens when you combine these. The total score is TF times IDF for each of the words involved. So in this particular case, the basically gets washed out of the score. And the important aspect of the score is contributed by diddle, because it's rare. And this document ranks pretty high even among the diddle documents because it contains diddle twice. That's a mouthful, but once you start applying the score to every single document, then that's how search gives you the right results, the results that you are interested in up top. In the interest of time, I will skip this one because I know that we are overloaded. And we'd have been even more overloaded if I showed you that other slide. So I always like to pause here. When we get overloaded, one thing that I find cleansing, therapeutic is play work. I look at this. You can't help but watch this and find a sense of ease and just kind of relief. And I think that's really true of like all clay working. Like here's another video that I really think is just spectacular. Just yep, that's therapeutic. We're gonna do that 2 times actually, and see all the worries of all those complicated slides are behind us. Very good. So that leads us into our third section, relevance and code search. As I mentioned, until I moved into data science, my work at GitHub was code search. And part of what I did, and I unfortunately don't tell nobody this, I wanted to do some of these changes to the code search at GitHub, but I ended up moving to another team before I got a chance to tackle all of the problems I wanted. But it gives you a good example of the way a relevance engineer, a search developer would move through a search problem and try to improve search on behalf of their users. All right, so we're going to do 2 things. We're going to fix the worst problem with code search, and then we're going to fix the second worst problem with code search, and we're going to call it a day. That's a very efficient day. Ideas, practical experience. What is it like to be a search engineer? So the worst problem in code search, I think, was captured very well by Angelos Katharpoulos. Forgive me, Greek people. So at GitHub, you implement code search, but you decided to ignore period, comma, colon, semicolon, slash, slash. Yeah, all these things. I'm having fun searching for definitions and implementations without being able to use the thing you have in code, namely symbols. And I agree with him. So let's see what happens in GitHub's public search right now, where you search for something that I know to exist in our application, the GitHub application. So search query in Ruby, this would be a Ruby thing. This should be like the definition of a class, and this is just anything that is inheriting from the class, right? Any class that inherits from search query. So we get the definition of search, whose first argument is query. Burp, that fail, that's a fail. This is a fail, it's got an underscore there. This is a camel case, is also a fail. More fail, hyphens is a new form of fail. And we've got just lots of failures. This is sad. We've got 20 pages of 20 results each of the wrong results for almost all of them. Somewhere, I guarantee you, this exists of those results, but people aren't going to go to page 17 to find them, right? Okay, so this is one of the main problems. And this is how I would look at fixing it. First of all, I would say, okay, well, just like in the previous section, we did the tokenization. We saw how an English sentence can be chopped up and turned into words and stemmed and all that stuff. There's got to be something that our current application is doing to get code into tokens, those final pieces, and it's not doing it right. And so I looked at the analysis chain, and the main ingredient for the code analysis is this right here. Basically, take take our input, which is a big code file, and split on these special characters. So if this is your input, this is our example. What happens when you split on every character we care about? Well, you get 2 tokens left, and that's all you get. You've washed out everything except for the things that actually just kind of look like English. You got search in position 1 and position 0, and query in position 1. Boo, that's why it breaks. Does that make sense? Thank you for your nods of agreement. So the fix is easy. Now, it's not obvious. This takes like looking at Elasticsearch documentation for a while and kind of getting familiar with the different like spells and incantations. You can chop it up like English. You can chop it up like Chinese. You can chop it up using your own patterns. And this is just another one of those things. Whereas this one splits on special characters, This is a totally different thing that takes a regular expression and captures the regular expression. So it's almost doing the opposite. Rather than chopping it up based on the pattern, it's capturing it based on the pattern. And the pattern here says, match anything that's word-like, match anything that's, or match anything that is not word-like, but is also not a space. We're explicitly excluding spaces for now, which is arguably not a good idea either, but it gets us a lot closer. So what happens whenever we analyze the user's query in this case is we're capturing all of them and we're keeping them in the right order. So we can do something like a phrase query, right? And we can say this is exactly what the user is looking for. There are computational costs to this. So, I mean, there's always trade-offs, but clearly I don't think this was a great trade-off. So I implemented the thing in secret. And I found out that it actually works quite well. Our highlighter is broken for reasons that I have no idea. But our first of the 27 code results, sorry, I had to redact some of this. Our 27 code results, you can still see how many there is. The first 2 on the page is exactly what we're looking for. The next 2 on the page is exactly what we're looking for. The next 2 on the page are exactly what we're looking for. And it goes on and on. And this is not 27 pages. This is 3 pages, right? So much better user experience. You can more quickly get to what you're looking for. So that's one aspect of a day in the life of a search, a relevance engineer. How it's kind of on the indexing side. On the indexing side, how do you massage it so that the search engine point of view corresponds to something that the users would be more interested in. The other thing is on the search side, the other side, instead of indexing, a query. So I should probably say that's the query side. The second worst problem, when I search for a function name, I almost always want the definition, not tests that use the function. Could you figure out heuristics to prioritize the definition above the test? Yes, we can, Brad. The problem here is alluded to. I'm sure everything has been fire hose, but was alluded to in the TF-IDF section, the scoring. When you score the word the, it has very high document frequency, therefore very low inverse document frequency, therefore very low contribution to the score. It doesn't matter very much. But if you had a document that was just like the, then inside that document, it has a high term frequency. In that it kind of offsets the issue of the document frequency. It scores more. So what we have here is actually kind of a problem with the term frequency side of that equation. If you have the definition of query in one file, how many times does that word appear? Probably just once. You're defining it. But if you're testing the query function in some other test file, how many times does that term appear? Well, you've got 20 tests for it, so you're calling it 20 times. There is a chance, and it's often the case, that the test document has much higher term frequency than the original definition, and so poof, it's at the top of search. Annoying to users. So how do we fix that? First of all, this is on the indexing side. We're going to add a new field. As we're reading through all the documents code, one of the side things that we can do while we're reading through the documents is we can dump out all of the definitions. This would not be an Elasticsearch thing. You'd probably do it outside of Elasticsearch. You'd parse the document as whatever language it is and say, okay, here's a definition, and you get like an array of like all the functions and variables and stuff defined in the file. Next, you would we can add a file type field. So whenever we index the code, we can say if it's a test underscore file, then it gets, field type, file type test. You can, if it's a markdown file, we'd say documentation. If it's a YAML file, we'd say configuration. And if it's, just normal like python.py or .java or whatever file we say, that's the implementation. Anyway, this gives us the opportunity, these two fields give us the opportunity to boost the appropriate document more. And in particular, to boost anything that is a definition inside an implementation file. So we have to modify the query to take advantage of these new fields though. One thing, let's say we've got a user looking for get value. This is like, say this is the current broken query that does not boost things appropriately. The score, kind of in cartoon form down here, the score is only based upon how well the content matches. So if I've got a document that matches exactly, and it occurs several times, then this gets boosted pretty high. This is a fairly high score compared to a document that's got get value once. Test is boosted above, implementation probably. So one change I can make to this query is to, I just kind of shove the previous thing up here. You must match get value, but you should also, this is like extra credit bonus score. You should also match get value in the definitions. If you happen to have a definition that is an exact match for that, then we're going to give you extra credit of 5. So your new score, if you don't match in the definition field, you just get the content score. If you match in the definition field as well as the content field, you get kind of extra credit for it. So boom, boost up. And the next thing, this is going to be hard on the eyes, but don't worry, we will wade through it together. The next thing is you can incorporate the score of fields around it. Okay, so let's see. This is the original query, but I've wrapped this inside. This is another one of the building block queries where you can take a query and combine it with another query. I've wrapped our original query inside this thing called function score, which says I'm going to take whatever the original score of this query was, and I'm going to combine it additively with whatever function or functions that you put here. And the function here is simple. If you have a match in the implementation field or in the file type field, if the file type field associated with this document is implementation, that's got to be better than file type is test or config or something like that. And if you happen to match, we're going to bump you way up 25. I just pulled these numbers out of the air since this is not tested, and you'll end up higher in the list. And so think about what this means for, let's see if I can do this in the air in front of me, for a specific use case. Let's say that I have a test file. I have versus I have an implementation file where this is defined. So a test file has a content score, and it's going to be a high content score because get value appears, 20 times. We're testing get value. But then I also have this other file which has get value once, but it is the file where it is defined. So since it is defined, we pick that out. It gets extra credit for that. And since it is in an implementation file, it gets a lot of extra credit for that. And based on those two boosts, I can't guarantee it goes above the test file, but there's a really good chance that on average, these type files are going to surface above the test files. And by analyzing how often the results are to my liking, we can modify these numbers and make it do, whatever we'd like. So, holy cow, in my eagerness to go quickly, I've gone above and beyond the Call of Duty, and I think we're at 40 minutes, 30 maybe? Wow.
We're good.
That makes me wish I'd done everything half as fast because it was too fast. But anyway, that's it. Let's chat. I've seeded the queries, the questions you can ask, but I hope you guys will speak up.
Yeah, there aren't any more questions in chat, but I hope if you have questions now's the time. And thanks, John, so much.
You bet. I'm going to quit sharing.
How much would you say your job is as a search engineer, or was as a search engineer, was playing around with regular expressions?
Very little of it, honestly, because the only place that you would use regular expressions is when you're doing really finicky stuff. Like I happen to give an example of it. It needs to be a tool in your belt. But most of the time you're doing more broader stroke stuff, like rather than writing a regular expression about how to split up text, usually you're saying, okay, well, this is English text. And so I just want to go through the standard analysis chain. Or maybe this is a particular type of field, like if you're doing code search, another field we have is the path. What file does the code appear in? And users sometimes want to search for everything underneath the path. So you can take the path field and you can chop it up into tokens of the full path excluding the end, the full path excluding the two endings. You can chop it up like that. Doesn't seem anything like English, doesn't seem anything like code, but that allows you to write queries so that people can match on, whichever level of that they want to. So you're doing a lot of finagling at the analysis step with like, how exactly do I want to chop it up so that I can make use of this at query time. And since this is just fun to talk about, it opens kind of the door to, you can really index a lot of unusual things in a search engine that you don't think about as being text. You can index points on a map, latitude, longitude, because points on a map can be turned into a geohash, which is a string, which basically you can chop up, just like I said. The full string is most specific, and you can chop it up, and this portion of the string is the giant square on the map. Cool. You can also index songs in terms of the tune of the song. And the way that I've seen this done is if the song goes up from the first note to the next note, then you record an up arrow. If the song goes down, you can record a down arrow. If it's the same note, the next note, you record like just a dash. And this vocabulary of 3 letters is usually plenty of enough information. So if you were to sing a song, have something that translated that into up, down, up, that language, you can search, actually, interestingly, songs in a search engine. And there's plenty of fun examples. Fingerprints is another example. I think it's great. Pictures, stuff like that.
So Scott just turned on his video. I thought that would get his attention there.
Yeah, so music applications are pretty interesting. In fact, so I don't think anybody wants to hear me talk about it, least of all the people that I'm involved in developing it. Potential kind of music searching kind of thing. Really planning on, essentially using like a Shazam kind of thing, like a method of signatures type of thing. But the idea of just having it be character based definitely had not occurred to any of us. And I'm going to file that away as like among the many possible options for making it fast and scale. Like, we don't know how to write Elasticsearch for audio, but it could be that translating into the text and then using all the joy of the amazing optimization from Elasticsearch and whatnot would actually be better than our sophisticated signal processing based thing that would be, not optimized. So that's thought provoking. Just file that away.
Do file that away. It's interesting. If I know the type of stuff that you would do, and we'd have to get in a conversation outside of this crowd, but you're going to take a song and you're going to turn it into like a point in vector space or something like that, right? And search engines actually aren't terribly good at that. And point in vector space is very good at certain types of things, like how close are these, what I just hummed to that point in vector space for that song. But with search, if what you can do is like, if the whole song, you could say like, here is some sort of fingerprint, which might be kind of a quantized point in vector space, a much lower vector space. You can say, you can turn a whole song into words. I just said simplistically up, down, dash. But as long as you have some set of consistent symbols that make sense on the query side and can match to the same space on the index side, then yeah, you can make super fast lookups for a big giant set of songs.
Noted. Thank you.
I have a question, John.
Yeah.
Of structuring different data sources. So if we have, say, like a transactional database, do we just transform that data into an Elasticsearch data store for free text search, and we maintain these two sort of systems for two different types of processing?
You said the magic word, so which was going to key in probably a little bit more of an answer than you asked for, but I think it'll be actually useful. You accidentally asked something you might not have known. Transactional. So if I take your question to mean SQL, like MySQL or something, then part of SQL's guarantees are things that Elasticsearch is not good at. And understanding where those are going to be very important. So Elasticsearch, let's see, MySQL is good at transactions. I have these 3 rows to change that are going to change. I want to make sure that either they all 3 change and we update everyone's bank account, or that none of them change and we, fire an error back so we can retry or something like that. But it's going to be transactional. The other thing that search engines are good at, the Elasticsearch is particularly bad at, is joins. Like I've got these tables and I want to just like stick these 3 tables together, match user on, their bank account, whatever. So let's go over both of those. Elasticsearch has no guarantees on transactions. You can have the first thing succeed and everything else fail. That's unfortunate, but just the nature of the way that the data is stored, it just comes with that. You'd have to change everything from the ground up to do it. There is benefits actually to doing it that way, in that indexing and searching are super fast. Basically, you just instantiate segment files at a time, and it's getting a little bit too far. It's cool. We can talk about it later. The other side of that is, you said that you have an application. What do I do? Do I just create a copy of it in Elasticsearch? You'll have to denormalize it first. Elasticsearch, they will sell you on the idea of join, just like every NoSQL data store has been doing for the past 10 years. Don't trust it.
Yeah.
Elasticsearch is really Lucene under the hood. It thinks about everything as just a long table, one long table.
But you do really create 2 separate data sources, data stores, one for search, which is Elasticsearch, and that's where, if customers are coming and want to search through order history, or users want to come and search through document history, like they'll hit that data source, but you've got your separate transactional database
Yes.
for the in and out, for the atomicity and the acid consistency, all that sort of thing. And you just have to create some transformation that moves new transaction records into a copy of them into your Elasticsearch store.
Bingo.
Right? Okay.
The search engine itself is a view, and an understandably slightly old, slightly unreliable view of the truth data. So you can either have something that listens to updates in your SQL and writes it from there, or something upstream that forks it to the 2 things. But every time you get the results from Elasticsearch, it sounds like in your use case, you don't quite trust them. You go back to the database for truth before you display it to the user.
Okay, cool. So like it is by design, like this is for search.
Yeah, it'll be good for what it's good at.
The right tool for the right job. Awesome.
Good question.
I'm curious, John, and really the whole group. I don't know how many, Scott, you asked, so what is Elasticsearch? I'm wondering if this is a first view of Elasticsearch. My main question to John is, who are the primary users of Elasticsearch? Are these data professionals? Are they software engineers? I mean, I know both, but where does this happen most often?
So that's probably an interesting question. I use search. What am I?
You're complicated. Yes.
As several of the old guard here knows, I've most of my career has been basically hovering data engineering and data science my whole career, and search is really just right. It's the fence line, because in the data engineering side, you've got to get all the data where it belongs and index it. But on the data science side, you're doing, kind of big blocky things like, this is English, how am I going to manipulate this to get it into the system? You're thinking about the data, and then you're doing really nuanced stuff at the query side how are the users, let's get a list of everything people searched for in the past day, what they've seen with their eyeballs, what they actually clicked on. Am I doing a good job? Let's start comparing the result sets. And so that gets into really, really data science stuff. So that's the, my brain said artisans. I'm not sure I'm an artisan. That's the people that work on the search type applications. But as far as the utility of it, the users of it, it's at every, Google is an unfortunately extremely good one. I hate them. They do everything I do so much better. Any e-commerce search that you've ever been to is a search engine that probably, like Tim was saying, it maps back to a truth of source data store underneath it. Your libraries, your any sort of records, like medical stuff. So there's no lack of them. They're everywhere.
I can share some interesting use case for this. I've worked with Elasticsearch during my summer internship. We developed a project for government, and during COVID time, they had a lot of scanned documents, and they wanted to search so many things. So basically, we did OCR and then name entity recognition, and everything was done in Elasticsearch, and then they used to search some entities.
That's another good example of indexing interesting types of document. It's a little bit different layer to slice it at, but
Yeah.
OCR, that means you've taken a photocopy and you
Yeah.
got basically searched through the text that appeared on the photocopy. And
Yeah.
OCR, when I started with search, was horrible. Like,
Yeah.
you might as well just type random characters. I feel it's improved a lot at this point, but I haven't had a chance to play with it recently.
Yeah. Now they have improved a lot.
I got time for one more question, apparently. How could machine learning factor into this to make your indexes better instead of having a developer come in and observe the hits and the misses? And that's probably like way beyond like intro to Elasticsearch, but as like a distant, what if?
No, that is the big question.
Okay.
So let's see, which direction do I want to take this? There's a couple angles here. There was something that I was interested in before I moved into data science proper, is basically Elasticsearch in all search engines that are the main search engines, at least Solar, Elasticsearch, they're going to have tokens. It's just words. So you don't have this notion of a vector space basically at all. Elasticsearch is bolting those on. So like there is a field type now where somehow you can do that, but I've never had a chance to play with it, and I don't quite trust it yet, because I think you have to iterate through every document. You can't use the fast part of what search is. So I was playing around with ideas like, could you cast something into a vector space, and then we're like deep learning, that's what it's going to do. And instead of comparing, the distance in this high dimensional vector space, or the cosine similarity or something like that, can you just chop up that really high dimensional vector space into tokens? They don't make sense. They won't be like, the quick round fox, but it'll be like symbols that whenever I index a document, it's going to match to whenever the document is searched. It goes through the same process of chopping them up and turning them into features. Now, I never got very far down my own research into that, but other people have been having quite a bit of luck. I haven't followed it as close as I would have liked to, but I think it involves throwing away everything we ever knew about search engines. So get rid of the tokens. Whoops, they're gone. And instead, it's going to be like crazy vector algebra stuff to match lots of documents at the same time. It's really cool because you can get the super fuzzy matching. Like I want all images that have a dog in it. Like there's just no hope for a normal search engine to do that. But it does miss, at least I think, maybe it's awesome enough at this point. I suspect there's always going to be a need for the search engine of the flavor I just showed, because there are so many applications where you need to find the document that contains this phrase, and that might not be a good application for casting it into a 200-dimensional vector space or something.
There were a couple of other questions on chat, and I lost my focus there. Scott, so can't you just run the words through an embedding encoder, which is?
Yep, cast them to a high-dimensional vector space, but you can't. It's not going to be meaningful to have, like, let's say you got 100-dimensional vector space, where the floating point number for each element. You can't really stick that in the search engine. So how do you take that thing and make it look like
What?
a word?
Why can't you stick that in a search engine?
Well, I can stick it in there as just pure text, but then if
Why can't I send a floating point number into the search engine? The search engine is just not built for floating point?
it's going to try, like Elasticsearch, consult the documentation a bit. They've done some interesting things with alternative data structures, but like even a single floating point number, like let's say very mundane application, I record the price in a price field, $7.32. The search engine up until really recently, and maybe I suspect even still now, when I quit looking, is going to chop up $7.32 as 7 and 7.3 and 7.32, so that whenever you type, I want something that's between these ranges, it's gonna try to play games with these tokens and match what's in there. So take the complexity of that and turn that to a 100 dimension floating point vector. It's just not gonna work. Now you can quantize stuff, and that's kind of what I was playing with earlier. You can say, well, this chunk of space is the letter A, and just do whatever you need to do to get like 10,000 tokens or 100,000 tokens out of that space. But it worked okay in my experimentation.
I need to make sure we respect your time. We're already a few minutes over. I want to allow people to disappear. Know that, and I'm assuming, John, your slides will be sent to me so I can share them with the crowd. That worked. Okay. Also, the video of this evening, probably more so for other folks. I would love to be in touch. Like I said, I would ask you, instead of me searching for all of you, Glenn Acree, connect with me on LinkedIn. I would love to connect with you face-to-face or before we have our next meeting. Seems like there was one other thing. Ravati had one last question. Hers was, how do we index images? Was her question there, I believe. Did I get that right? Yes.
So the real answer at this point is probably poorly, but you can do it. The better way to do it is probably going to be some approach with deep learning, cast it into the vector space that we keep alluding to. But we've played around with toy problems that sound just like the conversation we had. Basically, if you can take Elasticsearch thinks in words, or more accurately tokens. So if you can aim any type of analysis at a photo and take out meaningful chunks, then that becomes something that you can search over. For instance, like I can say, how much red is in this photo? How, describe the middle chunk of the photo and, have, different chunks. Like, how is the middle chunk different from this chunk? Or if you get really sophisticated, do something with deep learning magic sprinkles, and like it is explicitly said, there is a dog in this photo. It's, stuff like that. So that at that point, you might as well just do something else. But in any case, the pattern that I hope you've seen in the past 15 minutes is, if you can turn anything into meaningful tokens, it doesn't matter if a human can look at it and understand what it is, as long as the query maps to the same token space as the document that is indexed in that token space, then you can do some neat stuff with search. And that's kind of a neat intuition.
All right, it's difficult to say thank you on Zoom, but we do appreciate it. You're getting lots of thanks in the chat. Thanks for everybody being here, and have a good evening, and we'll all be in touch. But yes, thanks, John. Thanks so much for sharing.
Yep. Thank you all.
Have a
Thank
good week.
you.
Take care,
Bye.
folks.